Hello, everyone. My name is Noreen, and today I will be presenting my research paper presentation, which is based on improving the validation of machine learning systems in aviation safety. In aviation, even the smallest unexpected behavior can have major consequences because every decision depends on reliable information. As machine learning becomes more common in safety critical system, it's important that we understand not just how accurate these models are, but how they behave under stress during failures and in complex real-world conditions. My goal today is to walk you through the research gaps, the limitation of current testing methods, and a conceptual framework that aviation can use to more thoroughly validate machine learning system before deployment. So, to begin, aviation is an industry built on extremely strict safety standards. Traditional software in aircraft is predictable and goes through rigorous certification, but machine learning introduces a completely different kind of behavior. It learns patterns from data and doesn't follow fixed rules. So, aviation regulators have said they cannot certify machine learning unless we can properly test it under all the conditions an aircraft may experience. So, this presentation will explain why machine learning is challenging in aviation, what's missing in the research, and how we can move towards a safer validation approach. So, let's move towards the system overview diagram. This diagram shows how machine learning fits into the aircraft data pipeline. On the left side, if you can see, we have the aircraft sensors, the things like pitot tubes, gyroscope, if you can see, like airspeed, altitude, GPS, and engine monitors. All the data flows into the aircraft computer and then into machine learning models. The model job may be to detect anomalies, predict future system failure, or assist with decision support. On the right side, the model's output influences pilot displays, the alerts, sometimes even automatic system like autopilot. So the key point is that if something goes wrong at any stage, especially at the sensor level, the machine learning model may give an unsafe output. A model that behaves perfectly under normal condition might fail completely during turbulence, icing, or sensor blockage. So this entire pipeline must be considered during the validation process. So the next is the problem statement. The core issue is that mostly the existing machine learning testing tools are not built for aviation. They usually test small input variations or simple noise patterns, which is fine for cars or image processing, but not enough for aircraft. Aviation faces hazards that develop quickly and are often unpredictable. So things like icing, pressure fluctuation, unexpected wind shear, or sudden sensor dropout. But current machine learning testing does not evaluate how models react to these flight hazards. So, this makes it difficult for regulators and engineers to trust machine learning in safety critical functions. Next, we have why machine learning behaves differently. So, the traditional aviation softwares uses strict logic. If A happens, do B. So they have like alternate. Everything is rule based and deterministic. But machine learning is different. It doesn't follow rules. It learns pattern from the training data. So this means two things. The first one is machine learning models often struggle with condition they haven't seen before. And second, machine learning models can change output drastically with tiny changes in input. For example, a small change in airspeed or angle of attack readings might cause a machine learning model to misclassify a situation. So this unpredictability makes machine learning extremely difficult to certify under DO 178C or other aviation standards they already have. After that, we have literature review summary. So, in reviewing existing work, I found that machine learning is being used in many aviation related studies. For example, predicting pilot errors, classifying accidents, analyzing NTSB reports, detecting faults, and identifying maintenance issue. So these studies are promising and show how machine learning can help identify the hidden patterns. However, the main limitation is that these studies mostly test machine learning under normal and clean condition. They are not focusing on the rare situations. They rarely simulate hazards, failures, or extreme environmental condition. So although the result looks good on paper, we don't know how the models would behave during a real life emergency, which is the main thing about the flights because it always the lives of the people always depend on the software then. Let's move towards this comparison table of machine learning testing methods. So this slide presents commonly used machine learning testing tools, for example, Deep Explorer, Deep Test, and adversarial testing. So Deep Ghost, TensorFlow, these tools usually work by generating slightly modified inputs to see if the model behaves consistently. While they are helpful for computer vision tasks and they don't reflect aviation hazards actually. They can simulate things like pilot icing, sudden altitude changes, or multi-sensor conflict. So although these tools seem advanced, they cover only a very small portion of the risk that matters in aviation. And then we have machine learning testing frameworks versus aviation needs. So this table actually shows the mismatch very clearly. Aviation needs robustness testing, temporal modeling, sensor fusion analysis, subsystem interaction testing, and certification documentation. But existing tools can't test any of these. They mainly look at image coverage, input fuzzing, or tiny perturbation. This comparison makes it clear that aviation needs its own machine learning testing framework, which should be tailored for the aircraft system, which can handle all of these kind of situations or issues which didn't handle before. So we need a framework after looking at this table. That's what we realize. So the next slide is deep learning testing overview. And this graph like slide illustrate that deep learning model behaves well within their comfort, within their comfort zone. What is the meaning of this? The meaning is the data distribution they were trained on, they are working well on that. But their performance becomes unreliable when the input shifts even slightly. And that is the main issue in aviation. In aviation, these shifts happen all the time. Unexpected weather changes, sudden sensor noise, turbulence, or rapid transitions between flight phases. These can push the model outside its comfort zone. A little bit change is going to make the decision false. So this is why deep learning models must be tested against excuse me, against edge cases and rare conditions, not just normal data. So not just the machine learning, but deep learning is also showing some kind of situations which is not good for aviation. And why we are taking considering all of these factors because aviation always matters a lot in all the lives of the people because the lives of the people actually depends on the aviation systems. So next, move towards the research gaps. Here are the 5 major gaps identified. The very first one is no aviation-specific robustness testing. So machine learning isn't evaluated under hazards like icing or turbulence. This is what the meaning of the first one. So the second one is no temporal or sequential testing. So models are not tested across time or flight phases. They didn't test all the flight phases, converting from one to another situation. And the third thing is no digital twin simulation. What is that? The researchers rarely test machine learning in realistic aircraft environments. And the fourth one is no entanglement testing. So, no analysis of how machine learning errors spread to other systems like autopilot. So these things are not covered before. And the fifth one is no certification alignment. So the style evidence is not even being produced. So these gaps collectively explain why machine learning is not yet certified or certifiable for safety critical aviation uses. Next, we have this table, the research gap and incidents. So this table actually demonstrate how each gap is linked to real aviation accidents. While searching for the paper, I try to see two kind of accidents and which are like real life examples. So I put them in the table here. So for example, if you can see the very first one, Air France 447, that involved unreliable airspeed due to pilot icing, something robustness testing should detect. So the second accident is the 737 MAX MCAS accidents. Those showed what happens when a system relies on a single sensor and isn't comprehensively testing in failure scenarios. So these incidents make it clear that aviation cannot ignore hazard-based testing. We need these kind of situation in aviation. So these should be considered in the future framework. Let's move towards the diagram, sensor failure diagram. So this diagram explains how pitot tube icing affects airspeed readings. When the pitot tube freezes, it stops measuring pressure correctly. This leads to incorrect airspeed value being passed into the aircraft system and potentially into the machine learning. So obviously, when the incorrect values are passing, are going towards the machine learning models, it is not going to check the value is correct or not. It is machine learning models always give the results based on the values they got. So they don't know if it is correct or not. If machine learning hasn't been tested under these incorrect data condition, it can misjudge the aircraft state and that can lead towards a really big accident. So this reinforces why testing machine learning with faulty sensor data is absolutely essential. So these should be considered whenever we are trying to link machine learning with aviation. Next, we have our proposed framework overview. So this slide provides a high-level summary of the framework I'm proposing, which has 5 components. The very first one is hazard robustness testing, then sequential or temporal testing, digital twin integration, entanglement, or system interaction testing, and then certification alignment. Each component directly addresses one of the major research gaps. So the idea is to build a validation approach that reflects how aviation actually works. And let's move towards the digital twin diagram. Uh, this visual helps explain the concept of digital twin. A digital twin is a virtual aircraft that behaves like a real one. It allows us to simulate extreme scenarios like freezing, rapid descent, or turbulence without risking lives. Digital twins are becoming more common in aerospace engineering, and they are a natural fit for machine learning validation. Why? Because they allow repeated testing under controlled dangerous conditions. That's why this is the first thing which we considered while introducing our new framework. Next, we have entanglement testing. And why entanglement testing matters, these 5 boxes actually shows how different aircraft subsystems depend on each other. A wrong prediction from a machine learning model doesn't stay isolated. It can influence autopilot behavior, flight controls, and pilot decisions. So, this chain reaction is what we call entanglement. So, validation must include not only the machine learning model, but also how its output affects everything else. Next, we have our framework flowchart. So, this flowchart explains the complete validation pipeline. We start with the machine learning model and move it through 5 evaluation stages. Step 1 is the certification alignment, and then subsystem entanglement, and digital twin simulation, robustness testing, and then we have 2 examples. If we talk about the certification alignment, we did what we want. to happen in this framework is I document the test results in a format capable with aviation standards. So this prepares evidence needed for machine learning adoption. And if we move towards the entanglement testing, we check how machine learning output influence other aircraft system. A small machine learning error can create a large system level impact. So that is actually handled in entanglement testing. And then we have digital twin simulation. Here we place the model inside a realistic aircraft simulations to observe behavior during extreme or rare events that can't be tested safely in real life. Because we don't want to do like just go to plane and something is happening and then you are testing something over there. So it should be done in simulation, not in the real world situation, because it can cause a lot of people's life. And then we have temporal or sensor fusion, which can we test how the model behaves over time and across multiple sensors, since aviation operates in sequence, not the single snapshot. So then we have robustness. We intentionally expose the model to hazards like icing, turbulence, wind shear, noisy sensors values, and miscalibrated instruments. So we can do this to check how it is going to work there. So overall, this flowchart represents a holistic aviation-centered approach to machine learning validation, something current tools which is not already providing. So this is how this framework is actually supposed to work. And then we have realistic workflow for using machine learning and aviation. This workflow shows how machine learning should be integrated safely into aviations. It it starts with data collection, then data modeling, and because after you collect all the sensor data and flight data, we need to train our machine learning model using that data set and applying with different safety constraints. The very third step is validate using proposed framework. We can use this framework, which we already proposed, to check and validate all the machine learning algorithms if it is going to give us the correct answer or not. And then test in a digital twin, which we already discussed in last slide. So if you can see, like the first is data collection, then model development, and then we are moving towards the hazard-based validation, followed by simulation, and then documentation for certification. That is the last step after doing everything. So this ensures that machine learning is not just technically accurate, but also operationally safe if we combine this framework and the realistic machine learning situation. So next we have a use case, which is spider tube icing. This use case shows how the proposed framework can evaluate a machine learning model during pilot icing. We simulate the icing and hazard testing, then analyze the model's behavior during the timeline of the icing event, and then test the aircraft response in the digital twin and evaluate system interactions. This actually demonstrates how the framework catches dangerous behaviors early. So we want to catch all the things beforehand, not after, which is going to give us some kind of a benefit of having these kind of software. So next we have stall scenario visualization, which is like Python's stall scenario graphics. The visualization show how incorrect airspeed readings can cause aerodynamic stall. So if machine learning misinterprets airspeed or angle of attack data, it may fail to warn the pilot in time. That's why machine learning must be tested under scenarios where the sensor data is misleading. So we should train our machine learning model beforehand on not just the correct values, but on incorrect values as well. Then we have use case 737 max MCAC. Although this wasn't a machine learning system, the accident shows why validation must include hazard simulation and system interaction analysis. A single faulty sensor caused the system to repeatedly command nose down inputs. So, a strong machine learning validation framework would detect this kind of vulnerability before deployment if we don't want to have those kind of accidents in the future. Let's move towards our contributions. which is still on the way. Like I'm still working on it. So the contribution of this research are identify major gaps in machine learning validations, then mapping these gaps to real aviation incidents, proposing a structured aviation specific validation direction, then showing how the framework applies to real hazards, highlighting how future certification could integrate machine learning. So the work offers a practical path forward to safer machine learning adoption. And then we have the conclusion. In conclusion, machine learning has great potential in aviation, but it must be validated properly. That's how we know. We learned while doing all of this research. So, current machine learning testing tools don't reflect the complexity or danger of real life condition, the real flight, the in the real life, whatever is happening with crashes and everything. So, by addressing hazards, time sequences, digital twin simulation, subsystem interaction, and certification, aviation can move towards safer machine learning integration, but we need this kind of framework to consider all of those points for achieving this one. And if we talk about the future work involves implementing parts of this framework and how we are going to implement this in real life. And we need the data for that, which we don't have right now. So, building more realistic digital twins, collecting data sets that reflect real hazards, and working with regulators toward machine learning certification. And there is a lot of potential for improving in this area. Right now, the data set I have, that is NTSB, which is somehow doing some work, but it doesn't have all of those features to calculate or do all of this validation beforehand. If you want to find the hidden patterns, it has descriptive data, textual data. But these kind of situations can be handled by those data set. So we need a good data set for that as well. That could be the one situation for future work as well. We need to find out the data set, or we need to request someone to give us that data set to see how our machine learning is going to work with this framework. These are a few of the sources which I use throughout the research. These are not including all of my papers here. I right now I have like 16 papers which I use for my research paper, and I'm still working on it, so might be I will add something. And so it is included in all the research papers reference which I include in my research paper right now. It includes machine learning testing frameworks, aviation safety studies, and incident reports. And two of them I already mentioned in these slides. So after that, that's all for today's lecture. And if you have any question, you can ask me later. I will be happy to take any questions from you guys. Thank you so much.